Hey, it's Horner in. We're going to look at 2010, question number one. And this first one just is one that you've seen before. You've got a block on a table. It's connected to a spring. And the other end of the spring is attached to the wall. The block is released and follows a trajectory. So it's pushed back and then it follows out, comes across, and then falls down to the floor. And so the important thing here is to recognize that we do have a picture and we need to think about all the things that are happening. So the very first thing we're going to do is let's go ahead and solve part A. Part A says calculate the time, so we know we're looking for time, elapsed from the instant that it leaves the table. So it leaves the table. So it's starting here and it is going to stop here. So here we've got the start and here we've got the stop. So we just want the time. So obviously we're only thinking about moving in the up-down direction. We don't need to worry about left and right because in the left to right, remember Vx is equal to dx over t. And up and down, it doesn't have any original y velocity. So the original y velocity is 0. So we can say that dy is equal to 1/2 gt squared. So let's go ahead and calculate the time. You have to write down some sort of equation that recognizes that the distance in the y is equal to 1/2 the gravity times time squared. If you rearrange the equation rearranged is t is just equal to 2h all over g. Now we can plug everything in. So the very first thing we need to plug in is the height. So we're going to take 2 times 0.8 and we're going to divide it by our value for gravity, which is 10. And you should get an answer of close to zero point 0.4 seconds. This part would be worth 3 points. You would get 1 point for having some sort of an equation that describes motion just going up and down. You would get 1 point for making sure that you have everything plugged in right, and 1 point for the answer with the correct unit. For part B, it says it wants you to calculate the speed of the block as it leaves the table. So what is the speed of the block as it leaves the table? We know in this one that the amount of time it takes to fall, so remember the speed here, so Vx is the same as the speed here in the x, which is the same as the speed here in the x. We know that it traveled for approximately zero point 0.4 seconds, and it did that for a distance in the x equal to 1.2 meters. So from that, we can just use our really easy equation. Vx is equal to dx over t, so let's go ahead and switch this. And we're just going to say Vx, so let's switch to the right thing here. Vx is equal to distance in the x over time. Our distance in the x is 1.2 meters. Our time was approximately 0.4 seconds, and so we end up with 3 meters per second, and that would be our final answer. The next thing they want us to figure out is how far, or calculate the distance x, the spring is compressed. So to do that, we're going to go back to the equation for, um, we're looking at really the equation for conservation of energy. So we know that our original potential energy should be equal to our final kinetic energy. So because we have a spring, we're going to use the equation for the potential energy of a spring. And remember that is 1/2 the constant for the spring times the compression squared. And the kinetic energy here is equal to 1/2 mv squared. So we already talked about how fast it's moving from the last one. We know that it's 3.0 meters per second. We know that the mass for this thing is about 4 kilograms. So that's the mass. We're looking for how much it's stretched. So that's our unknown. And we know that for this spring, the spring constant is 650 newtons per meter. So remember the potential energy, the original potential energy, plus the original kinetic energy should be equal to the final potential energy, so PE final plus kinetic energy final. And in this equation, there's a couple of things we don't have in the end. One of the things we don't have, I guess, is we don't have any potential energy. And the thing we don't start with is any kinetic energy because the original speed here is equal to 0, and the spring is totally let go now of the object, so we don't have any potential energy anymore either. So let's go ahead and solve this. At this point, our potential energy we said was 1/2 k x squared, and that should be equal to 1/2 mv squared. So the final kinetic energy is this equation, and we know the original potential energy for the spring is this equation. Now we can go through and say, well, we have halves on both sides, so let's go ahead and get rid of both of those halves. And our equation now is kx squared is equal to mv squared. We want to solve this for x, so x is equal to, and then here we're going to have the square root of m over k, or mv squared over k. And if you want to, you can go ahead and reduce that v all the way down, so we have the square root of m over k, and then that's times v. I'm going to write it that way so that you can see what happens. Now we can plug everything in, so this is equal to the square root of 4 over 650, because that's our spring constant, and we're going to multiply that times the velocity, which was 3 meters per second, and so your x value here should be 0.24 meters. And that should be the end of this problem.